Hello, welcome to the third live session for the course Earth Science for Civil Engineering Part 1 and 2, which is taken by Professor Javedin Malik and myself, Ananya Mukherjee. I'm a PhD student in IIT Kanpur, Department of Earth Sciences. As in the previous live session, we had discussed about igneous rocks and some part of the sedimentary rocks and also minerals which form these rocks. So we had done up to sedimentary rocks classification based on the grain size, grain sorting, grain shape, and also some different kinds of sedimentary rocks based on these classification criteria. So now we'll move to the next one, that is how do you know whether sedimentary rocks are suitable for construction purposes as foundation stones or something or in those lines. So how are they suitable? So one of the factors that governs the choice of such rocks is the homogeneity or heterogeneity that is prevalent in the rock. So when we say homogeneous material or homogeneous rock, we mean that the physical properties of the minerals in the rocks and also the rock as a whole is equal. So it's the similar all across the rock. And heterogeneous or heterogeneity is caused in a rock due to the occurrence of different kinds of either minerals or the differences in the grain sizes and the differences in the grain shapes. So few of the factors which control this homogeneity or heterogeneity of rocks is the first one is a cementation. What is a cement? Cement is the material that is precipitated out and it fills the pore spaces between different sediments or mineral grains. So these what is the purpose of the cement is it holds all the grains or the rock fragments together. So cement is an essential part in most of the sedimentary rocks. These can be either precipitated silica material or calcium carbonate material or iron oxide. So varying from this material that is present as a cement can govern whether it is a good sedimentary rock for construction purpose or it's a poor choice for construction purpose. So what is the problem with the presence of cement is, suppose we have calcium carbonate as a cement. Okay, so calcium carbonate, as we know, is very easily soluble in water. So suppose you're building something and that area is prone to maybe there could be kind of it's prone to water seepage, or the construct or the thing that you're building is possibly suppose a dam, if you say, where you will that there would be a constant presence of water over there. So what will happen with the water and the foundation being something which has calcium carbonate as cement is, this cement, the calcium carbonate will start dissolving and the mineral grains will not be able to hold the strain that is present because of the the dam material or the water pressure on top, and it will start causing cracks in within the rock. So those cracks can be fissures, or the material would be dissolved and you would have a slippage of the construction that is on top. So these are few of the issues that we have due to the cement. Now, cement, if it is a silica rich cement, so what happens is with time this cement can actually solidify and become better, and it can decrease the porosity between the between the mineral grains, the pore spaces that we have. So what happens is, if the pore spaces are completely closed and the silica cement is very nicely formed, no kind of water seepage can occur, and even the dissolution of silica is not that prominent. Like silica is a very sturdy material when it comes to cementing material in the sedimentary rock. The next that factor that controls the homogeneity or the heterogeneity is the grain shape. So if you have rough edges, so that means that these edges can, very easily be adhered by the cements. It will take up, it will make less pore spaces, because the angular grains can arrange themselves in a way to reduce the pore spaces. So that is why angular grained sedimentary rock would be much preferable than a rounded grained this sedimentary rock. Now, based on mineral composition, we prefer having a rock which has, similar kind of chemical composition in the minerals across. For example, when you take a rock which has mostly silicate minerals, and especially if it is quartz rich minerals, so and also the matrix, that is a finer grain material, and also the cementing material are also of the silica composition, then it is a very homogeneous kind of a rock. So we can use this for both as a foundation and also as your construction material. So these are some of the factors which kind of they you can use to understand whether a sedimentary rock is useful for us or not. So based on we had already seen classification of all sedimentary rocks based on grain size and grain shape and sorting. Now, since sandstone and also limestone and shale conglomerate, these sedimentary rocks are actually found the most on Earth's surface. Around 75% of the rocks that are found on Earth's surface is actually sedimentary rocks. So it becomes essential to kind of classify the different rocks that we see based on different criteria. So over here we see the this diagram to your left is actually based on two different kind of factors. One is the percentage of matrix, and the other is the chemical or the mineral composition that you will find in sandstones. Pure quartz, or like above 90% of quartz, is actually very good for your civil engineering purposes. But as and when it starts the availability of feldspars, F is feldspars and L is lithic means rock fragments. Okay, so if the quartz rock is also composed of say feldspar or rock fragments, then they become homogeneous, as we had discussed before. So if we have pure quartz, it is a homogeneous, but if we have feldspar or rock fragments, it will slowly start becoming heterogeneous. And the same way, when we see the amount of matrix, if you have very low matrix, that is finer grain material, say over here like silt to clay sized material, or silt to clay also for that matter, in the rock, if you have very low amount of it, it will become it will stay homogeneous. But as and when the matrix amount starts increasing, it will move towards being a heterogeneous rock. So that is why classification of sandstones is essential. This is also another classification criteria, where the feldspars, the presence of feldspars is again kind of classified into two different criteria, that is plagioclase and say potassic feldspars. And even the lithic, that is the rock fragments, is also then classified whether you have sedimentary rock fragments or volcanic, that is igneous rock fragments or metamorphic rock fragments. And next then we have classification of carbonate rocks. Now these are also it is important to know the kind of carbonate rocks that we have. carbonate rocks, though not very feasible to be used as foundation rocks, but they are usually used in construction material and also building cement, also making cement. So we have two classifications. The first one is the Folks classification. What is a sporite calcite cement? Sporite is crystalline, that it looks like mineral crystal. Okay, and micrite matrix. Now this is not crystalline. It will appear like very fine grained material. So these are the two kind of material that can occur between calcium carbonate grains. Okay, now these grains can be shells, and these can be previously deformed calcium carbonate grains also. These are called allochems. So based on the percentage of micrite, okay, so if you have very you know if you have very less allochems, that is the coarse calcite mineral grains, then you will have micrite. Okay, pure micrite. But if you have more than 50% of allochems, then you will have a different kind of a rock. Like over here it's written biomicrite. Okay, it's written biomicrite. Biomicrite, why? Because the calcite grain that we are talking about is suppose shells. Okay, so if it is shells, then we know that this has formed in biogenic settings. So the micrite also that is developed between the allochems is also biogenic in origin. Okay, so this is one of the classification criteria. Then the next classification criteria is the Dunham's classification. Now this is very much useful when we have to classify hand specimen, like you have taken a rock sample and now you want to classify it. So the classification can be based on whether grains are present, the calcium carbonate grains are present, how much of it is present. So if there are very less amount of grains, it will be called mudstone. If there are more grains and a very less percentage of mud or the micrite sediments, then it is called grainstone. So this is another classification. So now suppose we have these sedimentary rocks. I have not named them till now. So which of these would be suitable? You are just seeing the rock and you're kind of first classifying them and understanding their physical properties first. So in the first rock over here in the extreme left, you have rock fragments and you have finer grained matrix. Now when you see this composition, you can very easily say that this is kind of a heterogeneous rock, because you see the rock fragments, the composition of the sediments are totally different, are two different ones. Then you see the grain shape, it is angular to subangular. Now since it is angular and subangular, if pressure is applied to this rock, suppose it's being used as a foundation stone, the foundation is of this rock and there is something built on top. So with pressure, the angular grains might arrange themselves in a way that the pore spaces get minimized and it can hold the pressure. Okay, and the cementing material is silica. So silica, again, silica cement is much favorable than your other cementing material. So in a way this is a favorable rock as if you want to use it as a foundation stone. Now in the next rock we can see that there are again rock fragments and finer grain matrix. So again there are different kind of this is not a very well sorted rock, that would be a poorly sorted rocks, because you can see different sizes of grain of the sediment grains. Now the grain shape is sub-rounded. So sub-rounded again means that this will not be the pore spaces or the cement will not minimize the pore spaces. And then you have suppose you have calcium carbonate as cementing material. So again, if the calcium carbonate is present, it is much more vulnerable to being dissolved and also weathered out. So that is why then this would not be a favorable criteria for us. Now in the third one, we have fine sand sized mineral grains. Okay, we can see the we can see the fine sized mineral grains. Okay, now we can say that these mineral grains are essentially quartz and feldspar. Okay, so quartz is a very sturdy mineral, as we had, it's a stable mineral. Okay, and also the cementing material is also of silica. So that is again a favorable criteria. So out of these three, we can say that this one and this one are favorable. Okay, and this one won't be favorable. Then the next one, if we say, okay, so over here we have sill sized clay minerals. Okay, now if you remember the previous lecture, we had discussed about different silicate structures that are found in silicate minerals. Clay minerals are silicate minerals, and they have sheet silicate structure. The sheet silicate structure can hold water in it. Okay, they are hydrous in nature. So this rock inherently holds water in its mineral composition itself. Okay, so that is not very favorable for us. Now we cannot see from our naked eye which kind of a cement is there. Okay, it can have silica, it can have calcium carbonate, and it can also have iron oxide. Okay, so depending on the cementing material also, the rock varies. Now in the right hand side sample, we see it's gray. Okay, but we having kind of conducting few tests, we see that this is a calcium carbonate rock. Okay, and since it's fine grain, we cannot really judge the grain shape, and the cementing material is also calcium rich cementing material. So out of these, based on these criteria, we can say actually kind of none of these are suitable as foundation rocks because of their inherent properties. This one is not suitable because it has clay minerals. Okay, so clay minerals will cause slippage of whatever construction you have on top, and calcium carbonate is also not good because it has the tendency to get dissolved easily. Okay, so these are about sedimentary rocks and how you can judge based on the different criteria, the classification criteria, and also the different textures. We can try to understand how any of the samples that we take, you can judge whether they are suitable for our use or not. Now the next thing is sedimentary structures. Now these are essential to know. Sedimentary rocks actually are very good records of past climate, past different kind of movements that are seen on the earth's surface, and also the different kind of geomorphological processes that have taken place due to the action of wind, waves, or glaciers. Okay, so sedimentary structures kind of give us an idea about how these things had taken place. So suppose you have what is called a normal grading. Suppose you take a rock, okay, you see there are coarse grains at the bottom, there are medium sized grains in the middle, and there are finer grains at the top of the rock. Okay, so you see a rock and you see coarse at the below, then you have the medium, and then you have the finer grains. So what this means is that the sea, suppose this rock was formed in a kind of marine environment. Okay, so we can understand by judging the sequence of the sediment sizes and also how they are arranged, we can see whether the sea had deepened up, that is the sea level rose, or the sea level fell. Okay, so actually normal grading gives us an idea about deepening of sea, and inverse shows a shallowing of sea. Okay, deepening of sea means sea level rise, and shallowing of sea means sea level fall. Okay, so this sedimentary structure is called graded sedimentary structure. It can be normal, it can be inverse. Okay, so this gives us the idea about the sea level rise and fall. Now what we see on the right hand side in the B figure, we can see that the sediments are kind of aligned, okay, like this. They are aligned over here. So this means that the current, okay, the current was flowing in this direction. The current of whether it has formed in marine environment or in river environment, or it has been formed due to wind. Okay. So on top again we see that this is a graded uh, this is a graded structure. Okay. Over here we can again see that this is a normal grading. Okay. Some common structures that we have are bedded, laminated, cross bedding. Now bedded means around more than 1 centimeter of layers, and laminated means the layers are less than 1 centimeter in size. Now we come to metamorphic rocks. So metamorphism is actually when pre-existing rocks, it can be igneous, it can be sedimentary, and it can also be metamorphic rocks itself. When pre-existing rocks on Earth's surface, they undergo changes in their uh, at that moment, whatever temperature and pressure conditions are, there is a change in it. Now the change can happen due to different things. Either there is a plate boundary, so you have kind of a subduction zone, or you have a collision zone, or it's a transform kind of a boundary. Okay, so it can happen over there. It can happen as a uplift of the rocks over there. It can happen if the the rocks are kind of pressed down due to different due to more sediments coming on top. Okay, so based on these kind of different situations where you can see changes in temperature and pressure conditions, we have different types of metamorphism. The first is cataclastic. Cataclastic is when you have faulting and folding, like either the rocks over there are getting folded due to your stresses acting on it, or it is getting faulted due to the stresses acting on it. So the material that is between the two rock blocks which are kind of moving against each other, so the middle portion, okay, between the two the rock blocks, you will find that due to intense heat over there, or intense kind of a pressure condition, the material between the two rock blocks would get metamorphosed. So myelonite is one example for it. Then you have dynamic. Dynamic is when there is high pressure. Okay, the pressure suddenly increases, and the temperature may or may not increase with this. So that is called dynamic. And then you have contact metamorphism. That happens when, suppose you have a surrounding rock. Suppose you have granite. Okay, now through some kind of a crack or a fissure in the granite, and due to uh, magmatic intrusion, okay, an igneous intrusion you have over there, it's coming out from the fissure. Now at below the earth's surface, due to this hot igneous intrusion, the rock around this intrusion will get metamorphosed due to change in temperature. Okay, it becomes heated, and you might have new minerals also over there, and the granite that is there will also get metamorphosed into different kind of a metamorphic rock. Then you have plutonic. Plutonic metamorphism happens when the rocks kind of they like at a subduction zone, the rocks are move towards greater depths due to, say, one plate subducting below the other. Okay, so at greater depths you have high pressure and high temperature, and due to that you will have a plutonic metamorphism, metamorphic rock. And granulite is a group of metamorphic rocks that kind of they are formed due to plutonic metamorphism. Then you have the most common metamorphism, that is regional. So it has both high pressure and high temperature, but the depth of this can vary. Okay, so it causes recrystallization of the parent minerals, of whatever minerals are present in the parent rock. They recrystallize into new minerals. The chemical composition might mostly stays the same. Okay, but the mineral will change due to regional metamorphism. And also we see different kind of structures and textures formed in the metamorphic rock due to regional metamorphism. So based on the types of metamorphism, these are a few questions. Suppose you are asked, like, which of the metamorphism causes almost none to little like new mineral formation? Can you guess which metamorphism would give us this? Like no new mineral formation. Okay, so the one is dynamic. Why dynamic? Because only pressure is acting in this kind of metamorphism, and with pressure mostly what happens is the structure and the texture of the of the parent rock is kind of changed. Okay, because there is no heat involved or no temperature change involved, recrystallization rarely occurs. So new mineral formation is very rare in dynamic metamorphic rocks. Okay. Now regional metamorphic rocks, regional metamorphism is also called thermodynamic metamorphism. Okay. So when we say thermodynamic, that means that it will include temperature, it will also include pressure, and it will also actually include fluids. So the correct answer is D. Okay, this is the correct answer, where the regional metamorphism involves both temperature, pressure, and the fluids that are present within the parent rock. Okay, now which of these places would you see severe degree of metamorphism? Now, in our first class, we had, discussed about different plate boundaries. Okay, so actually, at the edges of the plate boundaries, okay, where the plate boundaries are kind of moving against each other, or one is going below the other, or there is divergence that is happening. So, at these areas, you have the most severe degree of metamorphism. Okay, and suppose you are given different kinds of metamorphic rocks. So which of these would be formed by regional metamorphism? Regional is high pressure, high temperature. Okay, so it is actually nice. Okay, so now we see this sequence of metamorphism. We learned that there would be different kinds of metamorphism depending on how much pressure change is happening, how much temperature change is happening. Okay, so now what the next thing that we need to know is the sequence of metamorphism. Why it is required? So we can understand that how certain metamorphic rocks are formed, and it also dictates the minerals that would be formed in the metamorphic rock. Okay, so basic is that you can have igneous, sedimentary, or metamorphic parent rock, or it is also called protolith. Okay, then you have either pressure acting on it, or temperature acting on it, or pressure and temperature acting on it at different grades. Okay, so then you have metamorphic rock. So this is a sequence. Suppose you have shale, which is a sedimentary rock. Okay, with increase in pressure, slate will form. Okay, now with further increase in pressure, okay, you will have phyllite forming. Now further increase in pressure and some amount of heat also, like the temperature is increasing. Okay, so you will form schist. Now gneiss will be formed when the schist goes into a condition where you have high pressure and high temperature. Okay, then you will have the gneiss as the metamorphic rock that is formed. Now if we consider basic igneous rocks, now what are basic igneous rocks? Igneous rocks which contain mostly calcium, aluminium and magnesium silicates. They are usually dark colored rocks. Okay, so due to their mineral composition, okay, of the basic igneous rocks, a different sequence would be formed. Okay, so if you have high pressure, okay, you will have green schist forming. Okay, then you have further high pressure and some increase of temperature, you will have amphibolites. Then if you have high pressure and high temperature, okay, then you will have granulites. Then if you have very high pressure and temperature and at a much greater depth, a group of rocks that is called eclogite rocks are formed as the counterpart of the metamorphic rocks of basic igneous rocks. Okay, these are the sequences. So as we see that in the sequences, when we move from left to right, the temperature or the pressure is increasing. Okay, so increasing will be called prograde. Okay, suppose you have schist. Okay, now if the schist is later on, kind of it is uplifted. Okay, suppose from depth it is brought on top. Okay, due to the different again, now because it is coming on top, it might be getting temperature difference and the pressure. And suppose you will have because it is rubbing along against different rock blocks, okay, you will have metamorphism around those areas. Now the material that is over here, okay, it will kind of get either recrystallized or you will find the texture that is similar to phyllite forming over there. So that would be again, that would be called retrograde. Okay, so retro is reverse and pro is along the increase of the pressure and temperature conditions. So we have grades of metamorphism: low grade, medium grade and high grade. Okay, so these actually depend on the temperatures, temperature of the conditions where these rocks are formed. So over here we see that high grade metamorphic rocks are formed above 500 degrees Celsius. Okay, so then can metamorphism also occur at around 850 degrees Celsius? So the answer would be actually false, because above 800 degrees Celsius, the minerals that we see, they turn into melt. The last mineral that usually forms is quartz. Okay, so the quartz has very low, like it crystallizes at very low temperatures, so very low, around 800 850. Okay, remember Bowen's reaction series. So according to that, we can say that if the temperature conditions reach around 800 degrees Celsius, then the metamorphism will not occur, it will convert into melt the rock over there. Okay, so after learning the different grades of the rocks, we have something called metamorphic facies. Metamorphic facies is a group of metamorphic rocks which are formed under a similar set of physical conditions, chemical compositions, and usually each of these facies have a definite set of minerals that are found in this group of rocks, that is in this facies. Okay, suppose we consider amphibolite. Okay, so over here we can see that amphibolite, one few of the signature minerals that are found in the amphibolite facies rocks is say diopside, then you have hornblende. Okay, so diopside, hornblende, these are amphiboles, so these are found in amphibolite facies rocks. Now according to the temperature that is given here, you can understand which grade of metamorphism this would be, and the column headings of the three columns here, these are actually the parent rocks. Pellitic means, sorry, you have kind of sheet, the clay minerals, sheet silicate structure minerals. Okay, calcareous means calcium rich minerals are in the parent rock, and mafic means you have you have plagioclase, you have pyroxene, and you have amphibole rich parent rock. Okay, now as we had discussed eclogite. Okay, so if you see eclogite, it is forming at very high pressure, okay, and kind of moderate temperatures, but the depth at which it forms is very high. Okay, so few of the important minerals that are found in eclogites are omphacite, and also you have hypersthene and diopside. These are some of the signature minerals that are found in this facies of rock, metamorphic rocks. So suppose you are given this sequence, okay? Shale is the parent rock, which is a sedimentary rock. Then it is forming slate, then it's forming phyllite, then it's forming schist, and then it's forming gneiss. So as per what we discussed previously, we will try to see what would be the grade of this rock and what would be the type of metamorphism that is seen. Okay, so for slate, it is a low grade, that is it is forming at lower temperatures, and the type is dynamic. That means the pressure is the uh, active agent that is forming this rock. Okay, so the next is phyllite. Now the slate is converting into phyllite. That means the slate is undergoing low to medium grade rock, low to medium grade metamorphism, and the type of metamorphism that we see over here is dynamothermal. That is, you have pressure increasing, and also there is a temperature element which is causing the changes in the rock. The minerals will start to change. Okay, the kind of the structure that we see will change of the phyllite from the slate. Now the next one is schist. So schist is formed in a medium grade metamorphism and also regional metamorphism. So medium as in the depth is probably increasing a bit, and then you have high pressure and kind of moderate temperatures that are acting on phyllite, which is causing it to turn into schist. And finally we have gneiss, which is a high grade metamorphic rock, and it is also formed due to regional metamorphism, but the temperature and the pressure both are very high compared to the schist, and that is why schist is converting into gneiss. So the next we come to is metamorphic textures. Now what is metamorphic textures? It's the alignment of the minerals that are present in the rock. Okay, so the changes in texture of the protolith or the parent rock happens due to the different kinds of metamorphism. Okay, now when metamorphism is happening, suppose we are taking dynamic metamorphism in consideration or regional metamorphism. Okay, so you have pressure or stresses acting on the parent rock. Now this stress is not uniform. Okay, so if you have horizontal stresses and vertical stresses, okay, all these stresses are not uniform, and this kind of stress is called differential stress. Now due to this differential stress, the alignment of the minerals change. Now alignment of all minerals do not change. There are particular minerals whose alignment actually matters when it comes to metamorphic textures. What are these minerals? These minerals are called foliated minerals, and these are usually platy kind of thing. You can these minerals, when they occur in mineral form, they will usually you can pick it off, it will come out like a layer. Okay, so few examples are mica and also clay minerals. Now clay minerals, obviously you cannot really take the flakes out of it, but clay minerals, as you remember, has sheet silicate structure. Mica also has sheet silicate structure. So these sheet silicate structure minerals are usually called foliated minerals. Okay, so when stresses are acting on the rock, you will have different kind of alignment of these foliated minerals. So as you can see the in the example in the extreme left figure, you see these are foliated minerals. Okay, so these are in random directions. Okay, so this rock layer, okay, suppose the entire rock formation over here is undergoing compression, vertical compression. Okay, and the horizontal compression is low. Okay, it's not absent, but it's low. So these foliated minerals have a tendency to align themselves perpendicular to the stress direction, maximum stress direction. Okay, so then since we have vertical compression, the foliated minerals will take horizontal alignment. Okay, similarly if there is horizontal compression, okay, so these randomly oriented minerals would then orient themselves perpendicular to the horizontal stresses. So then you will have vertical foliation. Why foliation is important for us to know is because when we are considering such areas for as suppose foundation of our construction projects, we need to know in which alignment these foliation planes are. Okay, so if they are vertical, if you build anything on top, okay, so all these planes are actually planes of weaknesses. Okay, so these can cause slippage in the rock itself and also the construction that is on top. That is why when it comes to construction, uh, we kind of favor such kind of a foliation alignment. That is, you have horizontal. So if you put some if you construct something on top, the pressure will continue in the same direction. Okay, and the weakness planes will be perpendicular to that. But over here, since we are constructing something on top, the weakness planes, the slippage can occur in this direction, or it can occur in this direction. Okay, so this is not favorable. Now based on the occurrence or the presence of such foliated minerals, we have foliated metamorphic rocks and we have non-foliated. Foliated means that there are foliated minerals first of all, and they align themselves in a certain direction, and you can see this alignment in the rocks. Non-foliated usually happens is because firstly they do not, probably the parent rock does not have much of it. If there are, due to the metamorphism and the pressure and temperature conditions, these rocks these minerals recrystallize, and also since they are low in amount, they don't really affect the chemical composition of the formed metamorphic rock. And also the pore spaces of the non-foliated minerals is kind of eliminated, and the mineral grains fuse together as they recrystallize into a new metamorphic rock. So suppose we see these are few specimens. Okay, in the first we can see, okay, that there are some minerals and there is a certain alignment that is present of these minerals. Okay, so looking at this we can say that this is a foliated metamorphic rock. Okay, now in the uh, right hand side sample, okay, we cannot see any such alignment or any such foliation present. Okay, so because of that, then we will describe this as non-foliated rock. In the the picture at the bottom left corner, over here again we do not see any such foliation planes or any foliated minerals that are present here. Okay, so again this is a non-foliated rock. Now the last one, that is the right hand side corner, we can see that in the bottom part you can see that there are some layering kind of a structure seen over here. So when you see such layerings, so this would be called a foliated metamorphic rock. Okay, so after seeing how igneous rocks are formed, how they are classified, how they appear, the similar in the way of sedimentary rocks and also metamorphic rocks. Suppose now you are only given the description of a rock sample. Okay, when you pick up a rock, you don't know its name, you only can see, okay, the different kind of physical properties that is present. So suppose your first rock is green in color with fine mineral crystals visible, okay, and I will go a step ahead and call these mineral crystals that are visible as olivine group. So okay, so firstly when we are saying it's an olivine forms in igneous rocks, okay. So the first clue is there that it's an igneous rock, okay. It is green color. Now green color is very significant for one kind of rock, that is ultramafic rock, okay. Ultramafic rock, and the name is dunite, okay. So dunite is an igneous rock, it is rich in olivine. Now will we consider this for our civil engineering purposes? No. Why? Because olivine is the first rock to first mineral to form as per the Bowen's reaction series. So it is also the most unstable mineral, and it will weather very easily into different sedimentary or secondary minerals like serpentine, which are further vulnerable to next stage of weathering or erosion. So any ultramafic rock for that matter is not suitable, okay. Next rock we have is, suppose you find medium sized shells in it and it is embedded in white material, okay. So shells are formed of calcium carbonate, okay. So that is our first clue that this is a sedimentary rock, okay. And the material that is surrounding the shells is also white. So the white material is matrix and also cement. Now if it is white in color, it is most probably calcium carbonate. So again this is not a favorable rock. So this is supposedly called fossiliferous limestone. Fossiliferous why? Because we have shells in it, okay. So because of the presence of the shells and also calcium carbonate as the predominant chemical composition of this rock will not be used as a foundation stone. It can be used to make cement and other construction related material, okay. So the next one that we have is, we can see peach, white, grey colored minerals, okay. So these are you can easily identify the different minerals that are there, and it is a pheneritic textured rock, okay. Now since these are all light colored minerals, okay, we can say that this is a felsic rock, and also because we are using pheneritic texture, we know that it's an igneous rock. So it's a light colored igneous rock, okay. Light colored igneous rocks, the most probability of the minerals that are occurring in it are quartz, feldspar, okay. Quartz and feldspars are pretty much very stable, and they are useful to give us a better foundation rock. So this rock is granite, okay. So granite can be used for foundation and also as building stone. Now the next rock, suppose you see black and white bands of minerals, okay. So the minerals are arranged in black and white alternate bands, okay, and there are some peach colored minerals occurring between these bands, okay. So this, when we see black and white bands of minerals, black and white bands, or you can see layers, it can be either a sedimentary rock or an igneous rock. But in this you can see peach colored mineral crystals, okay. You can also see the black and white crystals very easily, okay. When you can see mineral crystals, it is most probably a metamorphic rock, because metamorphic rock is formed due to recrystallization. So the name of this rock is organ gneiss. Since it's a metamorphic rock, and we know gneiss is a very high grade metamorphic rock, and it is also formed at very uh, not stable conditions, sorry, at a much greater depth, and the minerals that are found are also pretty stable, that is quartz, and it has some kind of feldspar. So these are stable minerals, so we can use this also as both foundation and building stone, okay. Now the next one, suppose you have a round material, okay, which is embedded in brown colored fine to very fine grained material. Now big size round material and you have very fine grained material, okay. Now this can be both you know igneous rock and also sedimentary rock. Why am I saying igneous rock? Because we are only considering the size variation of the material. Now you see whether the material is crystalline in nature, or you can just see that they are like rock fragments. The big ones are either minerals or they are rock fragments. If they are minerals, then it would be igneous, and if they are suppose rock fragments, then you will call it a sedimentary rock. Suppose I can tell you that this is a conglomerate. Now we know that conglomerate has it's poorly sorted. It is poorly sorted, and the material is most probably say calcium carbonate cementing material, and the grain sizes are different and the grain shape is rounded. So we can say that this is not a good rock for foundation, okay. Why? Because due to the differences in sizes and also the shape and also the cementing material, you will not use this as a foundation because it's a heterogeneous rock. Now the next rock that we have, suppose it is very fine grain and it is black colored with small cavities, okay. This can again be either say an igneous rock, a sedimentary rock, and also a type of metamorphic rock which looks similar. But for sedimentary rock and metamorphic rock, black colored rocks are usually you can see different bands in it, but this one does not have bands, okay. And this also comes with small cavities. Suppose this is a vesicular basalt. Vesicular, the small cavities that are present are called vesicles, okay. Now this is an igneous rock, but because of its chemical composition, that is, it has mostly mafic minerals, pyroxenes, amphiboles, and also some olivines, okay. So these are not stable minerals, so these will weather very easily, okay. So in that sense, this is not a favorable one. And also if it has small cavities, okay, so if it has small cavities, these cavities can get filled with different kind of secondary minerals, which again makes it a heterogeneous rock, okay. So then this will not be useful as foundation stone or building stone. But basalt is very widely used for road construction, and also in while we build railroads, because because basalt has very high capacity to absorb shock. So these can be very well used for railroad construction and also the road construction, okay. So next few rocks, just like that, if we see some criteria, you have a peach colored fine grained rock, okay. Peach color and fine grain. Now you again see whether you can see mineral crystals or not. If you can see some mineral crystals, and if there are no bands kind of present, you can call it an igneous rock, okay. So this is an igneous rock, and it is a felsic rock because it's peach colored, okay. Fine grained rock, that means if it's an igneous rock and it's a felsic rock, and the grains are not very well developed because it's fine grain, that means it's an extrusive rock, okay. Now since it's a peach colored rock, most evidently you can say that quartz is one of the major minerals that is forming this rock, and that is why this will be a favorable rock to be used as both foundation and construction material, the building stone material. So we can use this rock, okay. So the next rock that we have is reddish pink in color, and you can see thin bands over there with red colored finer material, okay. When you see thin bands, the first indication is it will probably be a sedimentary rock, okay. Then you can see these sediments, either they are minerals, or they are different kinds of uh, sediments together, okay. So that will again give you an idea about whether it's a sedimentary rock or it's a probably a metamorphic rock, but metamorphic rock usually reddish pink in color is rarely found, so that is why we are going to lean more towards sedimentary origin of this rock. Okay, the red color, that is fine material that I'm talking about, that can be a siliceous cement. Okay, and now we know that this would be a sandstone, reddish pink color, mostly consisting of quartz. Okay, sand sized material in it, and you see thin bands because suppose it's a bedded structure of the sandstone, and the red colored cement is silica cement. Okay, so when we say that it's a sandstone, and sandstone is very well used as both foundation stone and building material. Okay, now the next one we have is thin black and gray layers fine grained rock. Okay, now this can be tricky because we have a sedimentary rock and we have a metamorphic rock which look very similar. Okay, so I will go ahead and give you the hint that this is a shale. Now shale, again, as we remember, contains a lot of clay minerals, sheet silicate structure minerals, that is mica. Okay, so these have a higher capacity of retaining water. Okay, so if your rock has water content in it, if it's high, then it will not be a favorable foundation rock. Okay, you cannot you cannot build very you cannot build construction uh, projects on top of shale, because shale has the tendency of slipping due to the water content of the in the minerals that are forming this rock. Okay, so this is not a good foundation rock. Next we have the white colored crystalline looking with green blue vein like features. Okay, so it is a crystalline rock. What do you mean by crystalline rock? Is that, you know, it has the appearance of a crystal. Okay, like a crystallized mineral. So it is white in color, it is crystalline looking, and it has green blue vein like features. Okay, now these green and blue vein like features can be due to some impurities present in the rock, or there was some minerals before which crystallized into these green blue kind of minerals. Okay, so such rocks are marble because it is white colored and it is crystalline looking. Okay, and these green blue veins are usually very much common in marble, as you must have seen in different kinds of places where marble is used for construction. Okay, so marble, as we know, Taj Mahal is built with marble, so this can be very well used as for construction purposes. Okay, and maybe not that well used for your foundation, because marble after all is calcium carbonate. Okay, in chemical composition, it depends on the conditions that are there where you are building this construction project. Okay, so that is the end of today's session. If you have any questions or any doubt, you can either ask right now, or I'll again share the resources. Just okay. Also, as you have enrolled in the NPTEL course, you can also find the recorded lectures and the updated Google slides by tonight. Okay, so you will find them in that tab which is called problem solving session. Okay, so you can go through these again. If you have any doubt, use the Google form link that I will be putting in the slides also, and also that I have shared in the chat box. Any questions, any queries, you can put over there. I will try to include it in the slides itself, or you can I will try to answer it in the next session. So the next session again will be held on next Tuesday, so please be present, so you can get your doubts cleared. Before I end, do you have any query? Thank you, Machindra. Hopefully it has helped you, and hopefully you can solve your assignments that is due tomorrow. I think week 3 assignment is due tomorrow, so hopefully this will help you in solving them. So the next session will be based on the next week's assignment, and it will mostly work upon the interior structure of the earth and the different seismological features and information that we have. So with that I will stop today's session, and hope to see you again next Tuesday. Okay.